Hello everybody. In this session, we discuss two-way analysis of variance model for fixed effects. The entire topic is divided into the following subdivisions. 1. Two-way layout. 2. Model description. 3. Decomposition of total sum of square. 4. Statistical analysis. 5. ANOVA table. 6. Comparing pairs of treatment means and block means. 7. Conclusion. Two-way layout. Consider the following example. The yield of milk may be affected by different treatments, that is the food diet fed to the cows as well as the different breeds of cows. Suppose that n cows are divided into k different groups according to their breeds, and each breed containing p cows, and p diets are given to these cows in each group. Now, our interest is to see the effect of p different types of food diet given at random to these cows on the yield of milk. Here the response variable, that is yield of milk, is affected by two factors, factor A, that is the diet, and factor B, the breed of cow. Such an experiment is called two-factor experiment or two-way classification. Let Yij represent yield of milk from the cow of the jth breed fed with diet I. I is equal to 1 to p, j is equal to 1 to k. The data can be tabulated as follows. The different diets are represented in different rows, the different breeds are represented in different columns, and the last two columns explains the treatment totals and treatment averages. The last two rows explains the breed totals and breed averages. Y11 represents the value receiving the first diet and from first breed. Y12 explains the value receiving the first diet and from the second breed. Y1k explains the value receiving the first diet from the kth breed. Similarly, Y21 explains the value receiving the second diet from the first breed group, etc. Y2k explains the value receiving the second diet from the kth breed group, so on. Yp1 explains the value from the receiving the pth treatment from the first breed group, and Ypk explains the value receiving the pth diet from the kth breed group. The treatment totals are given by Y1 dot, Y2 dot, etc., Yp dot, and the corresponding averages are explained by Y bar 1 dot, Y bar 2 dot, etc., Y bar p dot. Similarly, the breed totals are given by Y dot 1, Y dot 2, etc., Y dot k, and the corresponding averages are explained by Y bar 1 dot, Y bar 2 dot, etc., Y bar dot k. Y dot dot explains the grand mean. Here Y I dot represents the total of observations and Y bar I dot the average of observations under the ith level of factor or the ith treatment. Generally, the factor is represented as treatment. Similarly, Y dot j represents the total of the observations and Y bar dot j average of observations under the jth level of factors B, generally referred as the blocks or replicates or groups. Similarly, Y dot dot represents the grand total of all the observations and Y bar dot dot represents grand average of all the observations. These terms are explained as follows: yi dot is equal to sum of all the values receiving the ith treatment for all the k cells, that is summation j is equal to 1 to k yij, and y bar I dot is the average of ith treatment, that is yi dot by k, I is equal to 1 to p. Similarly, y dot j is the sum of all the observations corresponding to the jth breed or the jth group, that is given by summation I is equal to 1 to p yij, and the corresponding average is y bar dot j is equal to y dot j by p, j is equal to 1 to k. Similarly, y dot dot is the grand total, that is sum of all the observations given by double summation I is equal to 1 to p, j is equal to 1 to k yij, and the corresponding average is y bar dot dot, that is equal to y dot dot by n, where n is the total number of observations. In this case, it is given by p into k, because there are p treatments and k groups. Yij represents the jth observation taken from the ith treatment. Model description. Here two factors. In the above example, the diet and the breed are affecting the total response, hence we have two-way model. So, we define the model as yij is equal to mu plus alpha I plus beta j plus epsilon ij, where mu is the general effect, alpha I is the ith treatment effect, beta j is the jth block effect, and epsilon ij is the error term, which are independently and identically distributed random variables with mean 0 and variance sigma square. Observe that the response variable yij is the linear function of the model parameters. Equation 4 is also called the two-way analysis of variance model, because two factors, namely the treatments and blocks whose effects on the response is investigated. Next, we shall discuss the decomposition of the total summa squares. Consider the adjusted total summa square, double summation yij minus y bar dot dot whole square. First summation for I is equal to 1 to p, the second summation is for j is equal to 1 to k, can be written as by subtracting the quantity y bar I dot. So, the same term is added, and subtracting the quantity y bar dot j, hence the same quantity is added. So, hence can be written as double summation yij minus y bar I dot minus y bar dot j plus y bar dot dot plus y bar I dot minus y bar dot dot plus y bar dot j minus y bar dot dot whole square, adjusting the factor y bar dot dot also. We have three terms. I will call y bar I dot minus y bar dot dot as A, y bar dot j minus y bar dot dot as B, and yij minus y bar I dot minus y bar dot j plus y bar dot dot as C. So, now squaring this and expanding a plus b plus c whole square, we get the terms a square plus b square plus c square plus 2ab plus 2bc plus 2ac. So, expanding that, we can write the total summa square as k times summation I is equal to 1 to p y bar I dot minus y bar dot dot whole square plus p times summation j is equal to 1 to k y bar dot j minus y bar dot dot whole square plus double summation I is equal to 1 to p, j is equal to 1 to k, yij minus y bar I dot minus y bar dot j plus y bar dot dot whole square plus 0, because all the cross products tends to 0 in this case. Or I will write the total summa square as SST is equal to SSTR plus SSB plus SSE, where SST is double summation I is equal to 1 to P, j is equal to 1 to K, Yij minus y bar dot whole square can be written as double summation I is equal to 1 to P, summation j is equal to 1 to K, Yij square minus y dot square by n, which is the simplified formula for computation. I will represent SSTR as k into summation I is equal to 1 to P y bar I dot minus y bar dot whole square, which is sum of squares due to treatments and can be simplified as summation I is equal to 1 to P y I dot square by k minus y dot square by n. Similarly, SSB is equal to P times summation j is equal to 1 to k y bar dot j minus y bar dot whole square, which is sum of squares due to blocks or groups and can be simplified as summation I is equal to 1 to k y dot j square by p minus y dot square by n. Sum of square due to error is given by SSE is equal to double summation, one is for I is equal to 1 to p, second summation is for j is equal to 1 to k, Yij minus y bar I dot minus y bar dot j plus y bar dot whole square, and the sum of squares due to error is calculated as SST minus SSTR minus SSB. Observe that the total corrected sum of squares can be partitioned into a sum of squares of the differences between the treatment averages and the grand average plus a sum of squares of the differences between the block averages and the grand average plus a sum of squares due to random error. Hence, we can write total sum of square is equal to SSTR plus SSB plus SSE. Statistical analysis. In two-way ANOVA, we are interested in testing the equality of P treatment means as well as the equality of K group means. Hence, the hypothesis is, the first hypothesis is HA alpha 1 is equal to alpha 2 etc. is equal to alpha p is equal to 0, and the alternative hypothesis is HA1 at least one alpha I not is equal to alpha j for all I and j. And the second hypothesis we test is HB is equal to beta 1 equal to beta 2 etc. beta p is equal to 0, and the alternative hypothesis is HB1 at least one beta I not is equal to beta j for all I and j. Degrees of freedom of various sum of squares. Observe that the total sum of square is computed with n is equal to p into k quantities, which will carry n minus 1 degrees of freedom because we have adjusted total sum of square. Similarly, treatment sum of square will have p minus 1 degrees of freedom because there are p treatments, and block sum of square will have k minus 1 degrees of freedom because there are k groups or k blocks. Also, double summation I is equal to 1 to p, j is equal to 1 to k, Yij minus y bar dot is equal to summation I is equal to 1 to p, yi dot minus y bar dot, that is equal to summation over j is equal to 1 to k, y dot j minus y bar dot, which is equal to 0, and hence error sum of square will carry n minus 1 minus p minus 1 minus k minus 1, that is equal to p minus 1 k minus 1 after simplification degrees of freedom. Now, we will investigate a formal test of the hypothesis for HA alpha 1 is equal to alpha 2 etc. equal to alpha p is equal to 0, and for HB beta 1 is equal to beta 2 etc. beta p is equal to 0 against the respective alternatives. We have assumed that the errors epsilon ij are normally and independently distributed with mean 0 and variance sigma square. The observations Yij are normally and independently distributed with mean mu plus alpha I plus beta j and variance sigma square. Thus, the total sum of square is a sum of squares in normally distributed random variables. Hence, can be shown that SST by sigma square is distributed as chi square with n minus 1 degrees of freedom, and that treatment sum of square by sigma square is chi square variate with p minus 1 degrees of freedom. Similarly, block sum of square by sigma square is chi square variate with k minus 1 degrees of freedom if the null hypothesis is true. Further, we can show that error sum of square by sigma square is also chi square with k minus 1 into p minus 1 degrees of freedom. It also implies that SST R by sigma square, SSB by sigma square and SSE by sigma square independently distributed chi square random variables. Therefore, if the null hypothesis HA is true, the ratio FA is equal to SSTR by its degrees of freedom p minus 1 whole divided by SSE by its degrees of freedom p minus 1 into k minus 1, that is equal to mean treatment sum of square divided by mean error sum of square is distributed as F with p minus 1 and p minus 1 into k minus 1 degrees of freedom. Similarly, if the null hypothesis HB is true, the ratio FB is equal to SSB by its degrees of freedom k minus 1 whole divided by SSE divided by its degrees of freedom p minus 1 into k minus 1, that is equal to mean block sum of square divided by mean error sum of square is distributed as F with k minus 1 and p minus 1 into k minus 1 degrees of freedom. Equation 8 is the test statistic to test for HA, that is no differences in treatment means. Equation 9 is the test statistic to test HB, that is no differences in group means. The entire procedure now can be explained in the table form called analysis of variance table or ANOVA table. So, we have the first column explains the sources of variations, the second column explains the degrees of freedom, the third column explains sum of squares, the fourth column explains mean sum of squares, and the last column gives the F ratio. In two-way ANOVA, there are two factors generally denoted as treatments and blocks are affecting the response variables. Hence, the total variations are due to total, due to the treatments, due to the blocks and due to the errors. Hence, we have treatments, replicates, errors and total. The corresponding degrees of freedom for treatment is p minus 1, for replicate or block is k minus 1, for total it is n minus 1 and for error it is p minus 1 into k minus 1. In the third column, replace the corresponding sum of squares, that is for treatments we have treatment sum of square, for blocks replace block sum of square, for total replace its value total sum of square, and error sum of square is obtained by subtracting treatment sum of square and block sum of square from total sum of square. In the next column, write the mean sum of square, that is the total sum of squares are divided by the corresponding degrees of freedoms. So, mean treatment sum of square is SSTR by p minus 1, mean block sum of square is equal to block sum of square divided by its degrees of freedom, mean error sum of square is equal to sum of square due to error divided by its degrees of freedom. F ratio for treatments is FA is equal to MSSTR by MSSE. F ratio for HB is FB, that is equal to MSSB divided by MSSE. We reject HA and conclude that there are differences in the treatment means if FA is greater than F alpha p minus 1 and k minus 1, where FA is the computed value from equation 8 and F alpha p minus 1 into p minus 1 k minus 1 is the table value referring to F table at alpha level of significance corresponding to p minus 1 and p minus 1 k minus 1 degrees of freedom. Similarly, we reject HB and conclude that there are differences in the group means if FB is greater than F alpha k minus 1 p minus 1 k minus 1, where FB is computed from equation 9 and F alpha k minus 1 p minus 1 k minus 1 is the table value referring to F table at alpha level of significance corresponding to k minus 1 and p minus 1 k minus 1 degrees of freedom. Comparing the pairs of treatment means and block means. If we reject HA, that is if FA is greater than F alpha p minus 1 k minus 1, then HA, that is alpha 1 is equal to alpha 2 etc. is equal to alpha p is equal to 0 is rejected. This means that at least one alpha I is different from other effects which is responsible for the rejection of HA. Now, our interest is to find out such alpha I and divide the population into groups such that the means of the population within the groups are same. This can be done by pairwise testing of alpha i's as follows. That is, we test the hypothesis H naught A, that is alpha I is equal to alpha j, I naught is equal to j, against the alternative H1A alpha I naught is equal to alpha j. This can be tested using the following t statistics, that is t statistic is given by y bar I dot minus y bar j dot divided by square root of 2 times mean error summa square by k, which follow t distribution with p minus 1 k minus 1 degrees of freedom under H naught A. Thus, the decision rule to reject H naught A at alpha if the observed difference y bar I dot minus y bar j dot greater than t alpha p minus 1 k minus 1 into square root of 2 times mean error summa square divided by k. The quantity y bar I dot minus y bar j dot greater than t alpha p minus 1 k minus 1 into square root of 2 times mean error summa square by k is called the critical difference. Compute the critical difference for all the pairs and see where which pair y bar I dot minus y bar j dot is greater than t value, the table value, into square root of 2 times mean error summa square by k. So, that explains that pair is rejected. That means, those two treatments have a significant difference effects on the response. Similarly, in the case of rejection of H beta, if FB is greater than F of alpha k minus 1 p minus 1 k minus 1, then HB, that is beta 1 is equal to beta 2 etc. beta p is equal to 0 is rejected. This means that at least one beta j is different from other effects which is responsible for the rejection of HB. Now, our interest is to find out such beta j and divide the population into groups such that the means of the population within the groups are same. This can be done by pairwise testing of beta j's as follows. We test the hypothesis H naught b, that is beta I is equal to beta j, I naught is equal to j, against the alternative H1B beta I naught is equal to beta j. Again this can be tested using the following t statistic given by y bar dot I minus y bar dot j divided by square root of 2 times mean error summa square divided by p, which follow t distribution with p minus 1 k minus 1 degrees of freedom under H naught b. Here y bar I dot gives the mean of the ith group, y bar dot j gives the mean of the jth group. Thus, the decision rule to reject H naught b at alpha if the observed difference y bar I dot minus y bar dot j greater than t alpha p minus 1 k minus 1 into square root of 2 times mean error summa square divided by p, the quantity y bar I dot minus y bar dot j greater than alpha p minus 1 k minus 1 into square root of 2 times mean error summa square by p is called the critical difference. That means, whenever y bar dot I minus y bar dot j is greater than the right hand side quantity, we reject the hypothesis. That means, the pair of blocks or the groups I and j are significantly different. Conclusion. We have discussed in this lesson two-way layout with an example. We have presented the two-way analysis of variance model, stated the hypothesis to be tested and discussed the analysis. The entire analysis procedure we summarized in ANOVA table. We have discussed procedure to compare pairs of treatment means whenever null hypothesis for treatment is rejected. We have also discussed procedure to compare pair of block means whenever null hypothesis stated for blocks is rejected. Thank you.